Recording. So there's Mike's BluBots, and I've really got to try and zoom right in there to get some kind of idea of just how busy that is on there. There's a stationary version of one, although there's no reason it needs to be stationary, but that's something that we're using for a research project, and you can see there we're using magnetic resonant coupling as well as a couple of panels on there. Mike, tell us a bit about it.
Okay, so this is an example of energy harvesting. We have a solar panel that gives a maximum voltage of 0.6 volts.
That's 0.6. It doesn't need to be that big. It's just something that we had laying about.
And obviously, with 0.6 volts, we can't do anything. So we have to capture the tiny bit of energy you'll have on here and build it up in the super cap that's sitting underneath this board here. There's two of them. And so it takes this 0.6 volts and converts it to 3.4 volts over time. And what it can do then is this will harvest microwatts of energy. If we press this reset button down here, what we do is it comes alive, and what it's doing now is it's turned on its Bluetooth radio. And if we scan now, we will find that our BluBot has appeared in the Bluetooth, so we can connect to it now and actually drive this around. There's our BluBot there. And
so just from energy harvesting from a 0.6 volt solar panel, and it could be a fraction of that size, we can harvest enough energy there to not only drive the wheels around but also drive a Bluetooth transceiver, right?
Yeah, and have a real-time control of it. So we've got a left and right motor here with a motor controller that's on there that uses PWM to adjust the speed of the motor, so you can turn it and drive it forward and backwards. It's got a piece of EEPROM on there. It's got infrared communications for sending and receiving, so you can drive up somewhere and send a message. These are the photodiodes, so that it can detect where the light is coming from and move towards the light. And it was all an example of what can be done with a tiny amount of energy, and how to use that energy in a way where we're wasting as little as we can. Because that's the big key thing.
Yeah, well, it just goes to show that you associate things like wireless communication and so on with high power. Well, they're not low, ultra low power, but certainly by doing little tricks like turning them off temporarily and only using them intermittently, what you're effectively doing is stretching time. And if you stretch the time out, actually you can manage to do some pretty amazing things, and you've basically got a remote control robot there that's going to sleep most of the time but wake up periodically, communicate with the other robots and say where it is and what it's up to, how much power it's got in its battery banks and all this kind of stuff.
It's a good example now. This was hand soldered. It's a good example of what you can actually do with a bit of practice on the soldering, because most of the pins there you can actually hardly even see.
It's quite an accomplishment, really.
But it shows you can build a prototype, you can hand build it, you can get it working, and then you can send it off for production. So everything you're doing now is exactly what we would do in the real life to get a PCB from design into manufacture. Go through that process of simulation, breadboarding, build a prototype, maybe first on variaboard, get a single, one or two or three PCBs manufactured, they'll come back, populate the components just like you did with the amplifier, make sure it all works, send it off, order 10 million.
Mike, talk me through that other bot, because that isn't the original BluBot. That's the one that we use for research, isn't it? Yeah.
This breaks down the creature world into electronics. So what we have here is 3 tiers on this particular one. There is a 4th tier as well, and they're all named. So this one here is the brain, which has got a Bluetooth microprocessor in there. We call that the brain. This one here is a stomach. And what the stomach does is that has a energy store, and when we receive energy, it goes down into the stomach and sits there, gets digested, ready to be used as energy.
Which we can get from solar or RF in this one, so we can actually beam RF power into it to charge it back up again from some distance away.
And then that can plug into the legs, and the legs are a couple of motors. And what this does is this tries to take it scavenges any kind of energy that it can come in contact with. So in this case it's solar and RF, you know, so when you're using your mobile phones and everything, you're getting all kinds of transmissions. This is sapping a little bit of it and charging up its energy store from that, the Wi-Fi and all that kind of stuff. And it's just a demonstration of how we can just scavenge that wasted energy that's around us all the time and do something useful for it.
So your project is an energy scavenger, but it's scavenging from something that's generating maybe 3.5, 4 volts, right? And you're scavenging that because you can't run the motors from it directly because it doesn't have enough current. But what's clever that happens inside here is there's an energy harvesting IC. Just tell us a bit about that, Mike.
Yeah, this is a beautiful piece of design down here, and there's one in both of these. And what it does is it takes a tiny amount of current and stores it in a local capacitor, and when that capacitor's reached a particular level, it moves that energy from that capacitor into a larger energy store. And what that allows us to do is it creates a barrier between the tiny amount of energy that's coming in and the store that we're trying to charge up. So the tiny amount of energy might be much lower than the current level of our store, in which case it wouldn't actually add any more charge to our store, would it? Because our voltage level is always above it. And so it breaks it down in that way. And the whole IC is designed around minimum leakage, because we want to harvest microwatts here. And so there's a lot of things like resistor straps and stuff where you can set up the voltages you're looking to collect, so you don't overcharge the capacitor and things. And all of that is designed using very high resistance resistor. Do you remember the potential divider circuit where you have two resistors together to change the voltage? Well, if you can imagine, we showed you an example with like two 1K resistors. Well, this is doing it with two 10 meg resistors. And so when you do your Ohm's law on that, you can realise if you're using a resistor up in the megs, your current is very, very low. And that whole board is designed with that in mind, even to the point of the quality of the FR4 that's being used. All the components that are being chosen have made sure that their quiescent currents, the currents that they're consuming when they're not doing anything, is absolutely minimal. And so to actually measure the quiescent current of these boards, we need a picoammeter, something that can measure very, very low amperage.
And of course that's got a buck booster in there as well, hasn't it? So it's taking voltages from as low as sort of about 0.2, 0.3 of a volt and kicking those up to 3.5, 4 volts so that we can use them in the microcontroller and the wireless Bluetooth. Okay, brilliant.